Welcome to what is the first in what may be a long series of videos attempting to illustrate how conventional physics leaves a lot of questions unanswered in terms of describing causes versus just describing effects. So I'm going to illustrate that by playing some physics lectures all the way through, mostly. And all the way through all the subjects anyway. And I've chosen the lectures by Walter Lewin because they do have quite a few demonstrations and examples and experiments performed in them, which obviously I think is a better way to illustrate some of these functions. Physics is basically just could be described as stuff moving, and you're attempting to explain why it moves. And that is something we should be able to illustrate. We should be able to draw a picture of it. And their picture is a little messy. Dualities like wave-particle, I would argue almost paradoxical sources of energy like bending space or virtual photons, even having some things that are potentially moving through time, just stuff that really can't be the right answer. And so I'll attempt to explain possible alternative ways of looking at it that, in my opinion, are more reasonable and create a deeper, a harder, a broader foundation on which to build understanding of physics. So leave us proceed. If I can find the right video.
I'm Walter Lewin. My lectures will in general not be a repeat of your book, but they will be complementary to the book. The book will support my lectures, and the lectures will support the book. You will not see any tedious derivations in my lectures, for that we have the book, but I will stress the concepts.
There are quite a few tedious equations nonetheless, so I will avoid some of the unnecessary equations, just in the sense of beyond understanding a principle or variables that go into equations. There's no reason for this to create people who can do equations proficiently. That's really not the objective. The objective is to understand the concepts, to understand the mechanisms more precisely, to describe the possible mechanisms.
And I will make you see beyond the equations, beyond the concepts. I will show you, whether you like it or not, that physics is beautiful. And you may even start to like it. I suggest...
The subjective stuff was sort of an unnecessary approach in terms of some kind of attitude of beauty. Again, so much of physics is incredibly convoluted and has stuff that is just so close to paradoxical, this wave-particle battle that goes on for hundreds of years, that isn't in any way really resolved. None of that's very beautiful. That looks really ugly.
You do not slip up, not even one day. 802 is not easy. We have new concepts every week, and before you know, you may be too far behind. Electricity and magnetism is all around us. We have electric lights, electric clocks, we have microphones, calculators, televisions, VCRs, radio, computers. Light itself is an electromagnetic phenomenon.
So this was done around the year 2000, something like that, so obviously VCRs and all that stuff is a little outdated. But anyway, so there is no electromagnetic phenomenon. When he says light is an electromagnetic phenomenon, this is where they sort of go south in something very rudimentary. There's no evidence of any connection between light and magnetism. Magnetism can't bend a photon's a ray of light, and certainly electricity can't. So it's sort of important to kind of understand the definition of this electric thing and the magnetic thing. The magnetic thing does create what's called a field of magnetic force. Electrical things don't create anything called an electrical field. There's no field of electricity. There's either a pressurized atom or an unpressurized atom, but there's no field beyond the fact that you can have atoms in an atmosphere. And you can sort of understand that there's no field in the sense that electricity thinks that a vacuum is an insulator. It doesn't like a vacuum. It can't move in a vacuum, essentially. It has to burn atoms to create any kind of progression through a vacuum. So there's obviously no mechanism that makes it easy for electricity to go somewhere in the field. The only thing that makes electricity easy to travel somewhere is a conductor, something full of atoms. Atoms are the field that electricity flows through. So there is no electric field. There's only a magnetic field. It's one distinction. To try to illustrate this, if you understood the idea of there's forces and there's matter. The forces are all the things moving the speed of light. So this is why Maxwell made these associations. It's because light and magnetism and gravity move at the same speed. And so people think in some way they should be connected. And the connection is rudimentary and fundamental, not superficial as they've sort of made it. So anyway, you can call those force bits, little bits moving the speed of light. So I would argue that a photon is just little bits of energy with a distance between them, and that's their wavelength and frequency. There's no waves of electric and magnetic. The photons travel straight as little bullets, and there's a distance between the bullets, and that's all the information you need to describe a photon. The trick is the photons are essentially the energy inside of atoms. That is, they decide the energy of electrons, the pressure of electrons. So if I could illustrate the force bits, which are the electron and the proton, so there's two things. There's force bits, and the force bits have two characters. One's associated to electrons, one's associated to protons. So to simply illustrate this, imagine it as matter bits. The electrons and the protons, the only elemental bits essentially, are like ping pong paddles. Okay, so think of them as paddles. And the ping pong ball that can bounce between the paddles is the things going the speed of light, gravity, magnetism, and light. And really what you're doing is the force bits bounce between electrons and protons. Now if I have two electrons facing each other, the only bit that will bounce between them is, let's call the paddles black, and we'll call the ping pong ball black, is a black ball will bounce between them, electron force. If I use proton force, that is a red ping pong ball, it'll leave the paddles perpendicularly in some direction. So the only bit that can get trapped permanently, essentially, potentially permanently, is a black one between electrons. Now if these were two protons, the red ball is trapped, and any black ball that gets in here will leave perpendicularly. And that's the basic function. And you can sort of understand that with either one of these things, protons or electrons, they are instantly repulsive in the sense that if they have a black ball between them, the closer I bring them together, the more times the black ball will bounce back and forth. And each time it hits with exactly the same amount of force. So if it's getting hit 10 times a second, and I increase that by moving them together to 40 times a second, that's more energy that the paddle feels, and the paddle pushes out if there isn't pressure pushing the paddles together. So atoms are essentially the structure of these paddles in very tense geometry, where they have an equalization of the pressure pushing them to get towards the proton. The black paddles are being pushed towards the red paddles, and at the same time the black paddles are pushing away from each other, and that tension is essentially what holds atoms together, and that's magnetic tension. So hopefully you digest that, but you'll hear it over and over again, so you should be getting it as time moves on.
As radio waves are. The colors of the rainbow in the blue sky are there because of electricity. And I will teach you about that in this course. Cars, planes, trains can only run because of electricity.
Alright, these things, again, it's not really electricity, it's the magnetic component is just as important. So now we'll try to understand the difference between the electricity and the magnetic. So the electricity is the pressure, the ping pong balls between the paddles, and it's essentially always the electron paddles that get pressurized. So, and that pressure you could just realize as voltage. So the more ping pong balls there are bouncing, or the closer the electrons are to each other, that would be an atom that has high pressure. An atom that's negative, more positive because the signs are backwards, would be one where the paddles are further apart, so there's less pressure. The ping pong ball takes a lot longer to get for the impacts, less impacts per second. When two atoms of different pressure interact with each other, they always interact by one electron on both of them. So one electron will be the one that's the most influenced. And the electron that has the high pressure will push into the atom that has the low pressure. So the high pressure atom will essentially push into the low pressure atom, and by doing that, move those electrons a little bit, and that incursion into the other atom essentially increases the pressure in the other atom. So the two of them will come in as high pressure atom and low pressure atom. They'll interact a little bit, push into each other, and when they leave, they'll be both half of the average voltage. So they'll be the average voltage. So if this one was a 50 pressure and this was a 10 pressure, they'll hit each other and end up leaving as 30 and 30. And that's electricity. Magnetism is when that pressure happens, you change the shape of the atom. So the atom can be, when to pressurize the distance between the electrons, you have to move them closer together. You make the atom smaller. When you change the circumference of the electrons, you change the proportionality of the strength of the proton to the electron. So now there's not a perfect balance. So in a sense, you think of the proton being in the center and the electron is on this edge. Now if you're looking this way, as this proton has to have a lot more positive charge. We'll just use it for the sake of the language. It has to have more positive charge, so it's denser for it to be neutral at the surface of this electron, so to speak. So at this circumference that the electron's at, for this atom to appear neutral, this has to have it has to have so much force that by the time the force gets to where the electron is, it's the same amount of force as the electron. Then the atom will look neutral. So if you bring the electrons closer to the center, then the proton will appear much stronger. The atom will be imbalanced in terms of it will look charged. If you move the electrons further out, then the proton will look much weaker, and therefore the electron will look very negative. It'll look very electron imbalanced. And that's polarity. That changes the atom into something that's magnetic now, in that it will do this filtering thing where the the ping pong balls will be segregated. The black ones will be pushed one way and the red ones will end up going another way. And that's essentially magnetism. So there's a huge relationship between voltage and changing the magnetic charge or character of the atom.
Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could not see without electricity. Your heart would not beat without electricity. And you could not even think without electricity, though I realize that even with electricity, some of you may have a problem with that.
So again, it's not just electricity, it's the pressure, and the pressure is always changing the magnetic character of the atoms. And it just depends on how many atoms are having their character changed, and if where the character is being changed all in the same direction. So if you change the bias of an atom, and you do it with all of the atoms in the same direction, the effect of that bias is multiplied. And so a magnet is essentially a bunch of little atomic magnets inside, a bunch of imbalances all in the same direction that create the big red and black, which is essentially just pointing out proton electron. So the differences in the magnet, the red end, the black end, the north end, the south end, can be exactly correlated to the differences in the atom in the sense of the proton and the electron.
The modern picture of an atom is a nucleus, which is very small compared to the size of the atom. The nucleus has protons, which are positively charged, and it has neutrons, which have no charge.
Now, the smallness of the nucleus I have explained in other videos, but it just has to do with the fact that the nucleus contains a few electrons in it. And through this filtering process, the red force of the protons, the ping pong ball paddles. So you can sort of understand if there's two protons and there's force bouncing between them, red, they can't get closer because it's too much pressure. But if I stick a black paddle between the two red paddles, you can sort of understand that all the red stuff now will escape. So there won't be any constant reflections. And so the pressure will be greatly reduced. And that's why the protons in the nucleus get very close to each other, is because there is an outlet for the pressure. And that's why the nucleus is so small. When when you know that theoretically the electrons are hugely, they're in a huge distance from the protons. They have to be separated by a huge amount of distance. There's so much pressure between them, and if the protons didn't have that outlet, they'd have to be that far apart also, even further apart because they're more massive. So it's only because of this outlet. And the same thing would happen to an electron. If I had two electrons and they were repelling each other, if I stuck a proton between them, the two electrons could get very close to each other as long as there's a proton in between them.
The mass of the proton is approximately the same as the mass of the neutron. It's about 6.7 times 10 to the minus 27 kilograms.
Right, so these numbers are, they know neutrons decompose into a proton and an electron. So he's just kind of discounting the weight of the electron. And so he's basically just saying a neutron is a proton, but a neutron is a proton with a little electron stuck right on its surface. And that's the huge difference. The neutron makes it possible to have the protons get close to each other. It's the mediator.
The positive charge is here with the neutrons, and then we have electrons in a cloud around it. And if the atom is neutral, the number of electrons and the number of protons is the same. If you take one electron off, you get a positive ion. If you add an electron, then you get a negative ion.
Now, that could be true, in the sense that if you added, you can think about it. If I add something to that circumference, the circumference will get bigger. That means I've moved the electrons further away from the proton in the center, and now the strength of the proton from a distance will be weaker than the electron. The electron has been strengthened. And then if I pull an electron out, that means the circumference of the gets smaller, and it means that now the proton force is stronger relative to that circumference. And so I've changed it from a positive to a negative ion by changing the size of that orbit. Now, it's also true that you can change the size of the orbit just by extracting the pressure, that is, putting more pressure between the electrons, pushing them closer together. And you don't need to change the number of electrons. So this is a point where you could argue that there's a lot of assumptions built into their conclusion that it was the addition or the subtraction of an electron that creates an ion, when it could be argued that it's just the addition of pressure or the release of pressure that changes the size of the orbit, and you don't have to extract an electron or add an electron. So the idea that electrons are added or subtracted is a conclusion they drew from indirect evidence that there's no direct evidence that that's the way it happens. It's a change in pressure, whether the change in pressure is because you put another paddle in the group of paddles, or whether you just added more pressure.
The charge of the electron is the same as the charge of the proton. That's why the number is the same for neutral atoms. The mass of the electron is about 1830 times smaller than the mass of the proton. It's therefore negligibly small in most cases. All the mass of an atom is in the nucleus.
So if you associated mass with charge density, that sort of doesn't make any sense, because it makes protons 1,700 times more magnetic or more powerful than the electron. And you can't really say the charges are equal, and so something's wrong with the numbers somewhere, because that doesn't really make any sense. But it doesn't really matter, so we won't argue it here.
If I take 6 billion atoms lined up, touching each other, I take 6 billion because that's about the number of people on Earth, then you would only have a length of 60 centimeters. Gives you an idea of how small the atoms are.
I think the atom is to an apple what an apple is to the Earth. So there's as many atoms in an apple as there are apples that would fill the entire Earth. So you can understand, yes, atoms are very small. And the electrons are really, really small.
The nucleus has a size of about 10 to the minus 12 centimeters. And the atom itself is about 10,000 times larger, the cloud of electrons, which is about 10 to the minus 8.
Alright, so there's no cloud of electrons. They're in real positions. And in my opinion, they have to be substantially large, because they do collect. They're hit by photons fairly easy. You don't miss a billion of them and then hit one, and then miss a billion and then hit one. You hit them more often than that. But as the atom to the apple, as apple to the Earth sort of illustrates, there is an awful lot of atoms, so you can miss an awful lot of them. And so hitting one in a billion probably would be enough to be reflected. But anyway, how the circumference of the nucleus doesn't really have much to do with anything, but understanding the fact that there's there's all kinds of red paddles close to each other in the center, and then there's the black paddles at much wider spacing on the outside, is, in my opinion, a better way to understand it.
Centimeters. And if you line 6 billion of those up, you only get this much. Already in 600 BC, it was known that if you rub amber, that it can attract pieces of dry leaves. And the Greek word for amber is electron. So that's where electricity got its name from. In the 16th century, there were more substances known to do this. For instance, glass and sulfur.
Alright, and so this is where it gets kind of messy, because they're taking an electric phenomenon that is also creating a magnetic one. So when you pressurize atoms, or when you're putting more pressure between the ping pong paddles, you're also changing again the polarity of the atom. So you're making it into a little magnet. So at the same time you're increasing or decreasing its voltage, you're also changing its magnetic potential. So the two things connect to each other that directly. So you have to understand that any force that causes attraction or repulsion is a magnetic force, and the force that causes the conveyance of energy is the electrical part. So the electrical part is the movement of the pressure. The changing in the pressure changes the magnetic potential and changes its magnetism. And of course the magnetism has an orientation, a direction where it is more obvious. So think of the think of it as stretching atoms. So when you pressurize them or depressurize them, you stretch them in a direction, and that direction is essentially a magnet, a little compass needle.
And it was also known and written that when people were bored at parties, that the women would rub their amber jewelry and would touch frogs, which then would start jumping of desperation, which people considered to be fun, not understanding what actually was happening to the amber, nor what was happening to the frogs.
They understood. I mean, they had already done the little sparky finger thing. They had already worn their wool socks on the floor and picked up static charges and felt the little spark. So they knew that the frog probably wasn't liking it. So let's not pretend.
In the 18th century, it was discovered that there are two types of electricity. One if you rub glass, and another if you rub rubber or amber, for that matter.
Alright, so there really aren't two types of electricity. So it's just, this is, again, it's just inaccurate, I think, and it's just misleading because it creates this notion of positive electricity and negative electricity. And electricity is just a gradient of pressure. You can have zero pressure, but it doesn't make any sense. Zero pressure between electrons would be electrons at either end of the universe or something. It would be electrons infinitely far apart. And you can have a maximum pressure, which moves to infinity. Because as I move the paddles closer and closer together, you can understand that at the speed of light, there would be a distance where the impacts would be insanely high in number. And therefore the paddles couldn't possibly maintain that condition because the pressure, the amount of energy, would be insanely high. It would take all the universe to push the paddles together. The amount of energy would be so high. So the two terminate in infinities that aren't possible. So the range is somewhere between there. Very, very high pressure, very, very low pressure. But it can't go past a certain number. And the idea of a ground, you can sort of understand that the ground is just an average. So all the atoms that are connected to ground around me are all atoms that are touching each other. And they've shared their pressure. So the one that was at 40 and the one was at 10 turned into a 30, and then those 30s hit 20s, and that turned into 25. And it's all just the average amount of pressure. They've all been averaged. So if I take that average, then you can understand you can have pressure above the average and you have pressure below the average. So the positive pressure, which we see as negative, which we call negative, is extra pressure atoms, and the atoms of lower pressure than ground we call positive, but it's really the other way around. So a negative voltage is actually it's just so they labeled it wrong, and it just, the bad label is, they should fix it because it just really does break continuity in explaining something. But the point is, forget the signs, just understand there's atoms more pressurized than the ones of the ground, and then there's atoms that are less pressurized than the average of the ground. But there's no such thing as a positive and negative as a different thing. There's just less and more. So understand positive and negative as less and more, not two different things.
Let's call one A and the other B. It was known that A repels A and B repels B, but A attracts B.
Alright, so he's just saying A and B as electron-proton. The repulsion, as pointed out, is just because you have black paddles with a black ball bouncing back and forth. If I put a red ball in, the red ball escapes, no pressure. So only the black balls can pressurize electrons, only the red balls can pressurize protons. That is, force them apart or create energy. So they have their own force that they're sensitive to, and the opposite force, proton to electron opposite, is essentially ignored. It doesn't have an effect. It leaves in a perpendicular direction. And so this creates the opportunity to create high pressure between things and low pressure between things. So if the pressure gets low between them, the external pressure, the other force effects, pushes them together. So in simple truth, when two magnets move into each other, what's happening is the red forces are leaving through the black forces are leaving through the red, very low pressure between the magnets, and gravity is pushing them together. The stronger force of gravity.
And it was Benjamin Franklin, without any knowledge of electrons and protons, who introduced the idea that all substances are penetrated with what he called electric fluid, electric fire. And he stated, if you get too much...
So it wasn't a bad analogy, but it would have been better just to say pressure. And we now commonly associate the word voltage with a pressure. And that's all it really is. It's an amount, a volume. So in the sense of saying it's full of a fluid or full of a fire is a volume, and that makes sense. He mislabeled which ones were high pressure and low pressure, which has now ruined the plus and minus signs.
Of the fire, then you're positively charged, and if you have a deficiency of that fire, then you're negatively charged. He introduced the sign convention, and he decided that if you rub glass, that is an excess of fire, and he called that therefore positive. You will see later in this course why this choice, he had 50% chance, is extremely unfortunate. But
what you rub really doesn't matter, because all the processes is that when you're doing this friction thing, you obviously can kind of understand that that's a pressure act. You're causing pressure changes in the substances you're rubbing, and one of them will depressurize, one of them will pressurize. You're forcing atoms into each other more, and by doing that you're making the atom move, and by making the atom move you're making the electron seem like it has more pressure. You can sort of understand that the electron has pressure between the paddles, the ping pong ball, but if I move the paddles, that's sort of cheating, right? It's not just the paddle pressure, it's not the ball pressure anymore. I'm moving the paddles. So when one atom hits another atom and the atom has momentum, substantially more momentum than the other atom, obviously it'll seem like it has more ping pong ball pressure than it has. So that's what's going to get exchanged. So when you rub something with friction, you're banging atoms into each other, and in a sense fooling the atoms into thinking there's more pressure than there is. They pressurize. The atom movement turns into voltage. It turns into pressurization of the atoms. Sort of explaining why thermocouples create electricity.
Have to live with it. So if you take this fluid, according to Benjamin Franklin, and bring it from one substance to the other, then the one that gets an excess becomes positively charged, but automatically, as a consequence of that, the one from which you take the fluid becomes negatively charged.
Technically, the fluid isn't held in all the atoms, so most of this is static charge, which are charges that happen on the surface atoms. The surface atoms, you could sort of understand that the surfaces are always different. You know, trying to think of some kind of mechanism to illustrate that, but the membrane is always different than the stuff inside, kind of thing. So surface atoms are in a different condition. And the truth is they're easily pressurized or depressurized, whether it's an insulator or a conductor. If it's an insulator, it just means that the atoms don't connect to each other in a way where they're able to share their pressure, where they're able to the electrons are able actually to push into each other, and the pressure can move from atom to atom. So insulators, the atoms are far enough apart, are immobile enough where they can't quite bang into each other, and therefore they never share pressure. And so any pressurized atoms on surfaces can be very high, very different, and the pressure won't be neutralized. It'll just sit there on those atoms. So the surface atoms can be pressurized, and the interior atoms will know nothing about it. They won't change. A conductor, it's exactly the opposite. The atoms are very well connected, and every time you pressurize one atom, one electron, the pressure moves very rapidly through all the atoms. So that's sort of the difference between a conductor and an insulator. And again, there's different ways to hold the fluid. And static charges means you're just holding the fluid on the very outside of the surface. not inside the substance, where in other substances the fluid or the pressure is in the whole conductor. And so you have much more volume or amperage, much more depth to the pressure, a lot more of it. Spacebar.
And so that's the whole idea behind the conservation of charge. You cannot create charge. If you create plus, then you automatically create minus.
A bad thing to write is a law. I mean, because obviously you're creating charge in very subtle ways and through this exchange process. But again, you can convert one form of energy, the motion of an atom, into the pressure between electrons. So you can create charge essentially by transferring energy from one form to another form.
Plus and plus repel each other, minus and minus repel each other, and plus and minus attract.
So that's all he says. He doesn't say why they do any of that. Okay, so it's just written as a law. This is what it does. But he doesn't explain any force bits that do any of that, any mechanism. So I've explained, offered you an example of a force mechanism that the ping pong balls. So he's just saying black paddles repel black paddles. Red paddles repel red paddles. But he's not explaining how they do that or why they do that. And they do it for a specific reason. The electrons repel each other because there's something between them forcing them apart. There's a force.
And Benjamin Franklin, who did experiments, also noticed that the more a fire you have, the stronger the forces. The closer these objects are to each other, the stronger the forces. And there are some substances that he noticed which conduct this fluid, which conduct this fire.
Alright, so he went from two different subjects. So he's just explaining how when you move the paddles together, you're creating more of this force, more of this fluid, more of this pressure, just by proximity. And you can sort of understand, yes, proximity matters, because if I push paddles into each other, I increase the amount of force inside, because I'm increasing the amount of time something moving at the speed of light will bounce back and forth. It's kind of obvious.
And they are called conductors.
Alright, so the conductor and the insulator sort of explain the differences. One allows the pressure of an individual atom to be shared with the other atoms. The insulator doesn't allow the pressure of an individual atom to be easily shared with the other atoms. It's much harder. It's not impossible, it's just harder.
If I have a glass rod, as I have here, and I rub it, then it gets this positive charge that we just discussed. So here is this rod, and I rub it with some silk, and it will get positively charged. What happens?
So again, he's going to take one set of atoms, and he's going to bang them into another set of atoms. And one set of atoms is going to think it has a certain amount of pressure, but it really doesn't. It's just the movement. And the collision is essentially going to decide one atom's going to be incurred upon, and the electrons are going to be pressurized closer together, and the other one is going to relax as if it thinks it's a new average. So they think they're exchanging an average. So if they're moving fast, if they just slowly bang into each other, then they average. If one bangs into the other quickly, then they think they averaged, but they really didn't. This one averaged higher. The one that bounced off averages lower. And that's the why one gets pressurized and one depressurizes.
Now to an object that I bring close to this rod. And I will start off with taking a conductor. And the reason why I choose a conductor is that conductors have a small fraction of their electrons which are not bound to atoms, but which can freely move around in the conductor. That's
okay, so that's the traditional idea of how electricity moves, is because the electrons move. But that's really not what's happening. The electrons only move a little bit in the sense that they push on the paddle. So there's two paddles here, there's two paddles here. The paddle over here pushes onto this paddle over here, and that's the extent of the movement. The movement is very small amount of movement in the electrons that's just transferring pressure from one atom to the other atom. That's a conductor. There's no idea of a free electron involved. The only thing that's involved is the electrons are connected to each other, where in insulators they're not very connected, therefore they can't transfer pressure. Now he's using a conductor that's just a silver on a balloon. So it's a very thin conductor, okay, that has a huge surface area. And the only part, technically, that's going to get charged is that surface. It's the wrong way to say it. The balloon is it's not, obviously it's not neutral, but it's not connected to ground. It's not grounded. He has previously placed a charge on it, so he's made it negative, okay, for the purpose of the experiment. So he's touched it with something of low pressure and imposed low pressure on all those surface atoms. So all the atoms of that conductor have absorbed the low pressure, and their high pressure has been averaged down. So they were of a certain pressure, ground, to start with. He touched them with low pressure to pull the pressure down. So now it's low pressure. It's going to put pressure on the rod. That is, he's going to pressurize those atoms. And so now the two will be attracted to each other. And the reason why they're attracted is magnetism, though. That's the part I didn't say. So obviously, when I said before, when you pressurize the atoms, you change its magnetic potential. So if you go very high pressure, you're making it more magnetic. If you go very low pressure, you're making it more magnetic, because you're imbalancing the atoms. You're making them into polar atoms, which means they're like compass needles now. They have an orientation. And it's the orientation, the magnetizing of the atoms, that is, they're orienting, that is going to create the effect of the motion. The motion is magnetism, not electricity. The motion is being caused because they will be of opposite, or they'll be of the same magnetic potential. So if they're of opposite magnetic potential, that is, the balloon is going to have more, the protons are going to be closer to the surface and electrons are inside. The rod is going to have electrons on the outside and protons on the inside. And so there'll be opposite magnets. Magnets turned in opposite directions, and they'll pull towards each other.
Characteristic for a conductor, for metals. That's not the case with non-conductors. There, all electrons are fixed to individual atoms. So here we have a certain fraction of electrons that can wander around.
Alright, so there's no wandering around, and the difference between the insulator and the conductor is not that one has more free electrons, it's just the fact that they can communicate. The atoms communicate more directly or less directly, their pressure.
What's going to happen that the electrons want to be attracted by these positive charges, plus and minus attracting.
Alright, I can qualify that. Understand that in a system, the atoms are kind of jiggling and moving a little bit. There's also electrons, like infrared radiation electrons, photons, that are bouncing between the atoms. They're essentially a conduit that allows the atoms to communicate. So I guess I should have said this is a matter of proportion. The amount of electrons that are facilitating the communication between the atoms is so small that you can't associate it with current. It really just has to do with that, again, the exchangeability. But the electrons can facilitate that. So I should say that that metals do have the capacity to keep in their system these free electrons that would communicate between the atoms, and that insulators would be void of those electrons that would do that. And the insulators are also insulators against heat for that reason, because it's essentially heat. The mechanism that helps make things hot is the fact that the electrons start moving around, jiggling, they're hitting more often because the atoms themselves are also moving. So the electrons are moving, they're hitting things that are moving. That obviously increases the rate of reaction. It increases the rate at which things will reflect. It increases the number of hits. Again, it's all about hits. It's all about how many times something hits something else. How many times a force bit hits a material bit. How many times a force bit hits an electron or a proton. So first re-clarification where I said something a little too emphatic. There are free electrons, but they're just facilitating the exchange of pressure between atoms. The electrons that are free aren't pressurized. The atoms are.
And so some of these electrons which can freely move will move in this direction, and so the plus stay behind. This process we call induction.
Alright, so that's not really what's happening. The electrons don't actually migrate. All that changes is the atoms line up with their electron. Their shape has been changed, as pointed out. So they're pointing all in the same direction, where the electron heavy end is at one end, the proton heavy end is at the other end. And that lopsidedness can be flipped one way or flipped the other way.
You get sort of a polarization, you get a charge division. It's a very small effect. Perhaps only 1 in 10 to the 13 electrons that was originally here will end up here.
So 10 to the 13, 1 in 10 to the 13, which is something like 1 in a trillion. So obviously it's conceding it's a small amount of electrons, but the electrons really aren't what's causing the effect. The polarization of the atoms is what's causing the effect. The pressurization of the atoms.
That's all it takes. So we get a polarization, and we get a little bit more negative charge on the right side than we have on the left side. And so what's going to happen is, since the attraction between these two will be stronger than the repelling force between these two, because the distance is smaller, and Franklin had already noticed, the shorter the distance, the stronger the force. What will happen is that if this object is free to move, it will move towards this rod.
So he didn't really explain how it moves, in the sense that he's just saying, well, the positives aren't repelling as much as the negatives, so it just doesn't illustrate where the energy came from to move the thing. And the energy comes from gravity. The force on the outside will push them together, because there's less force between them now, because the plus force is leaking out of those little minus signs, and the minus force is leaking out of the little plus signs. No balls bouncing between the paddles.
And this is the first thing that I would like you to see. I have here a conductor, it's a balloon, a helium-filled balloon, and I will rub this rod with silk, and as I approach that balloon, you will see that the balloon comes to the rod. I will then try to rub with that rod several times on that balloon. It will take a while, perhaps, because the rod itself is a very good non-conductor. It's not so easy to get charge exchange between the two, but if I do it long enough, I can certainly make that balloon positive, then they're both positive, and then they will repel each other.
Alright, so he's basically going to just try to neutralize, that is, create more averaging. He's going to take something that's got a high pressure, and he's going to keep hitting something with a low pressure, and he's going to keep trying to feed the pressure from one surface to the other. One of the surfaces is going to be a conductor, but one of them is going to be an insulator, so it's going to be a little tricky, because you have to kind of turn the insulator and get the pressure off of it. It's on the surface, and it doesn't just all flow like a conductor. So you have to kind of just take it off in little pieces. Well, you'll see that, no doubt.
But first, the induction part, whereby you will see the balloon come to the glass rod.
So the balloon had been previously charged negative. He's positively charging the glass rod in the sense that he's pressurizing, or in this case depressurizing. So the balloon has excess pressure, he's taking the rod and making it under pressured atoms, and now he's going to put them in association with each other, and so it's basically just saying I'm putting the red end of a magnet and exposing it to the black end of a magnet, and you get the attraction. And you get the attraction because the red stuff will go out the black and the black stuff will go out the red. No pressure, the two things will move towards each other. No inside pressure means the outside will push them together.
These experiments work best when it is dry in the winter. They don't work so well when it is humid. So,
see, if he used another balloon with the opposite charge, so instead if he took the glass rod and charged another balloon the opposite charge, then you could see that it's gravity or some other mechanism, because both balloons would move towards each other. It wouldn't be like one moves towards something else. It would be both balloons would just go towards each other.
good time to teach 802 in the winter. Okay, there we go. This should be positively charged now. And the balloon wants to come to the glass. You see that very clearly?
So it's just a negative magnet moving towards a positive magnet. Just a red end moving towards a black end of a magnet. So it's essentially two monopoles. He's created a monopole of pressure on the balloon and a monopole of pressure on the glass rod that are the opposite pressure. So he's made essentially a giant electron and a giant proton, and he's basically just showing you what electrons and protons would do.
Come on, baby. Okay, so now I will try to get this balloon charged a little, so there is a change of electrons that go.
So it was already charged. What he's really doing, again, because his rod is positive, which means low pressure, he's basically extracting the pressure from the balloon. So as he rubs it, he lowers the pressure on the rod, touches the balloon, the rod gets pressurized. He rubs that pressure off again, to low pressure, pulls some more of the high pressure off the balloon. So he's extracting the high pressure off the balloon by contact.
From the balloon to the glass, and the glass it's not a conductor itself, so it's not always so easy to get charge exchanges. Okay, let's see whether I have succeeded now.
So again, the charge on the glass is all around it, so he's just trying to get some of that low pressure part of the glass to hit the high pressure of the balloon. And so it doesn't matter where he hits the balloon because it's a conductor. So he's just creating averages. So he's hitting the rod has a bunch of 10 pressurized atoms on it, and the balloon is 50 pressurized. And he's hitting the 10s onto the 50. All of the atoms on the balloon will start to reduce because they're a conductor. So they all start going down to 30 and 25 and then 20. So each time he does it, he knocks the average of the balloon down a little bit more, until he finally gets it to be equal to the charge on the stick. So now they both have the same 40 number.
In making the balloon positively charged as well as the glass rod. If that's the case, then the balloon is not going to like me.
Or 10 number in this case. The rod was the low pressure. See, it's just so bad with the broken plus and minus sign. The rod was the low pressure. He reduced the pressure of the balloon. Now they both have like a 10 pressure. So now the atoms, again, their atoms are lined up in the sense that the balloon has the same polarity. That is, the electrons are facing the outside, and the rod, they're facing the outside. And so now it's black paddle, lots of reflections. They will move away from each other.
The balloon will now be repelled, and you see that very clearly. To show you now that there are indeed two different kinds of electricity, if I now rub with cat fur, by tradition we do that with cat fur, I don't know why, by tradition we use silk for the glass.
So again, he just said it, two kinds of electricity. It's just kind of a wrong way to understand. There's just higher than ground and lower than ground, if you want to call them two kinds. So but it's just linear. There's low pressure and high pressure. They aren't two kinds. They're an amount. A lot and a little. So he shouldn't say there are two kinds. There's, again, the ground is what fools us all, because the ground is huge. The planet Earth is the ground. The surface of the Earth is the average number. So we're stuck with a very strong average. And that strong average makes us think that everything that's a little bit warmer is fundamentally different than anything that's colder. And it's not fundamentally different. It's just one is above the surface and one is below the surface, if you want to use that analogy. It's not fundamentally different. It's just, well, that's more fundamentally different, actually. It's not a good analogy. The ground is an arbitrary middle. So it just doesn't, it just fools you into thinking above is one thing and below is another thing. They're not different things. They're just more or less of something.
So if we do this with Catfur now, then this becomes negatively charged. Remember, there were two types of electricity, and since that balloon is positively charged, now the balloon will come to me. And there it is. Now it comes to me. So you've seen for the first time now clearly that there are two different kinds of electricity.
So again, the electricity didn't make that happen in the first place. That was the magnetic component. So the atoms were all distorted by the pressurization in their shape. Their change in shape made them into magnets, and the magnets have an orientation based on whether they're pressurized or depressurized. If they're depressurized, they become more positive on the outside. If they're lower pressure, they become more negative on the outside. And so it just changes the magnetic character of the surface. And so the two magnets reacted to each other.
Positive charge chosen by Franklin on the glass rod, and the negative charge on the rubber. So now you may think that if I approach a non-conducting balloon with a glass rod, and I have a non-conducting balloon here, you may think now that this balloon will not come to the glass rod because there are no free electrons. So these electrons cannot freely move, and so you don't get this polarization, you don't get this induction.
So again, it's really, that's not the case, and it just means that the surface atoms are in a sense conductive and the interior atoms aren't. So it's just basically a rule like that, that it can't be transmitted through the material, but the exterior atoms can be pressurized or depressurized. So an insulator isn't a perfect insulator.
That is not the case. And this is actually quite subtle. You have to look now at the atomic scale. If I take an atom like you have here, you have positive charge, and you have the electrons here in the cloud around the positive nucleus. If I bring a glass rod, positively charged nearby, then these electrons, which are stuck to the atoms, they cannot freely move like in conductors, however, will spend a little bit more time on the side where the glass rod is, because they feel attracted by the glass rod. Whereas the nuclei, if anything, want to go away from the glass rod. So what you're going to see is that, in a way, if I started off with a spherical atom, let's suppose this were a spherical atom or a spherical molecule, then what will happen is that you get sort of a shape like this. And
so that's the pressurization. That's exactly what's, and the pressure is what's causing that. So the pressure distorts the shape of the atom. When the atom's distorted in shape, it becomes magnetic in terms of having polar, in the sense that the proton and electron have a sidedness. More over here, less over there. But the electrons really aren't moving around the atom. You don't need that model to make this work. They're magnetically held in tension.
Electrons spend a little bit more time here than they spend here, and that means that I have actually polarized that atom.
See, in a real orbit, that wouldn't happen, in the sense that when things orbit, even though they speed up when they get close and all that kind of stuff, the center, they're still spinning around. They're still spending the same amount of time on one side as they are the other side, technically. So it wouldn't make any, it wouldn't work. merely misshaping an atom if the movement of the atom, the orbit, was what you were stretching. A stretched orbit wouldn't create the phenomenon. The phenomenon is being created because there's a differential in the distance. The electron is now closer to the surface and further from the proton. So again, it's back to my argument that the distance between the electron and the proton decides what you sense over here. If I move the electron closer to the proton, then you can sort of understand that now the proton is the dominant force. If I move the proton further away from the electron, now the electron is the stronger force. So I change what the atom looks like by changing the distance between the proton and the electron. It's a subtle but important difference.
The electron spends more time on this side of the atom than on this side. I have also created the phenomenon of induction, and I therefore expect that this side becomes more negative.
So again, it's not about how much time they spend on that side. It just has to do with the fact that the electron is now further away from the proton. And being further away means you've unequalized their force potential. When they were a certain distance, they looked the same, because one was first. It's like me taking a big object and a smaller object. And if I move them a certain distance from each other, I can make them look the same size. I can move the bigger object further away, and it'll look the same size as the smaller object. That would mean the atom looks neutral. But if I move the smaller object closer, now this object is bigger than this object, even though that's technically the bigger object. It's that kind of thing.
And that side. And I can show you that in a nice way with a transparency whereby I have plus and minus signs, and I have equal number of plus and minus signs. So they represent neutral atoms. There you see them. Boy, a little dirty, but let me see, I can clean it a little. Okay.
So this illustration is more accurate than his description, because obviously you're going to actually see the distance between the electrons and the protons change, and that's what's changing the magnetic effect. It's not about time, it's about distance.
Okay, so here we go. So notice there are equal amount of pluses and minuses. So think of the plus and the minuses as one neutral atom, just a representation. Now I'm holding a glass rod on this side, which is positively charged. And so each atom, the electrons want to go a little bit to this side, and so the nucleus stays behind.
So he just says they want to. He doesn't explain why they want to, what's causing them to want to. And what's causing the effect is that the electrons and the protons having a red and black paddle means you're automatically low pressure, because all the black stuff will go out the side of the red paddle, all the red stuff goes out the side of the black paddle. No pressure, the outside pressure will push them together.
And if each atom does that, this is what's going to happen. And now notice what you end up with.
So in this sense, so this part of the illustration is inaccurate in the sense that that doesn't happen. The atoms don't shift like that. So it's really just the fact that, because this is a surface phenomenon, again, so he's just basically showed a conductor. He hasn't shown what an insulator is doing at all, because the insulator is not capable of doing that, because the atoms aren't connected. But anyway, what's really happening is the stretch. So he should have just pulled them halfway, pulled them just a little bit, and you'll automatically make the black part be further away from the red part. So all you had to do was shift it a tiny bit, and you would see all red on one side and all black on the other side. He didn't need to make them jump a whole atom. So he jumped them a whole atom so he could create the illusion that he's created a row of electrons on the surface. But there is no row of electrons on the surface, technically, and there's no absence of a row on the other side. So he didn't need to move them that far to create the effect.
In the middle of the substance, plus and minuses cancel each other out again. But on the right side, you have created a negatively charged layer, and on the left side, you have created a positively charged layer. And so in a way, you have again induction. So even in the non-conducting objects, this side will turn negative and this side will turn positive. And therefore, if I approach a non-conducting balloon...
So he won't have a transparency here probably for a conductor, because there'd be no way for him to use this kind of format to explain what happens. But it's really just about a subtle, tiny change to make the thing more electron-y than proton-y.
With a glass rod, I will also see the balloon come to me. And so I can easily show you that. It doesn't make any difference whether I choose glass or whether I choose rubber. I can do it with both. Non-conducting balloons always have a potential problem. The potential problem is that
it's already charged. So first he has to neutralize the charge if he wants to show high pressure to neutral or low pressure to neutral, which is the same as low pressure to high pressure or high pressure to low pressure, because the neutral is going to be relatively high or low. So first he has to turn it into something of a known charge. So what he's going to attempt to do is ground it. He's going to attempt to take the ground that he's connected to and get the ground all grounded on his body, get all the atoms neutralized to the same charge. So he's trying to get the static charge off his hands. There might be some static charge on the hairs or on this or on that. So by rubbing his hands together, he's basically saying atoms make the same charge. And then he's going to take that pressure, which is the ground pressure, let's call it 25, and he's going to touch the balloon and make it 25. So now 50 will be above 25 and 10 will be below 25, plus minus.
They can be charged by themselves, just like the metal balloons can be charged by themselves. However, if I touch the metal balloon, then any charges there will immediately flow through me to the earth. We will understand that later, because this is a conductor. Remember, the electric fluid is conducted by a metal, but not by a non-conductor. So with this, it's more difficult. Even if I kiss it and touch it, it's not clear that I can take all the charge off.
Well, it is sort of clear that if you did it in some rational way where you just touched it all around, you know, touch, neutralize, touch, it will get most all the charge to be the same charge on the surface. So there's still, the point would be is that if he does it imperfectly, there'll still be parts of the balloon that are high pressure and parts of the balloon that are low pressure. So it'll have a mixture of charge. So the balloon will turn to reflect the fact that parts of it are positive and parts of it are negative. So you might see that. If he had lines drawn on the balloon, you might see when he brings the rod to it, the balloon will turn, because there's certain parts of it that are going to be lower pressure or higher pressure than other parts.
In fact, by doing that, I may even make it worse. Let's hope that it is not charged too much, and let's approach it with this glass rod and see whether I can convince you that indeed it's coming to the rod. Not because of the free electrons, but because of that process. Oh boy. Oh. And it should also do the same.
So, you couldn't see it, but the balloon probably did rotate a little bit, because the balloon has an uneven, imperfect charge. But clearly the rod is of the high pressure, the neutral is lower. The two will attract because, again, it means the atoms are bent different. One has the protons showing, one has the electrons showing. So it's just like bringing a black end of a magnet towards a red end of a magnet.
With rubber, I hope, if it were negatively charged, they go away. It does go away, so it is negatively charged. You see that? By touching it, I actually probably charged it. And there's not much I can do about it.
So the problem is he can't get the rubber rod to go to a substantially lower charge than the ground.
Very difficult to get charge off. I already had a suspicion when I approached it with...
He probably should just push the broom down to the desk and rolled it on the desk, and maybe that might have worked better, because he's probably wearing shoes that are a little bit insulated. He's probably not at perfect ground himself. he's not well grounded. You should put water on the floor. Salt water.
Glass, it was too eager to come to the glass. Still negatively charged. That's the way it goes. It's not because the demonstration failed, but it's because the balloon is charged.
Yes, the demonstration did fail. So, but yeah, the point is that if the negative has less potential, it's just clear that, you know, ground, the average, is there's more room above ground, high pressure, than there is room to go below ground pressure. It's always a little bit harder to create that negative low pressure, the low pressure. The low pressure is always the harder pressure to create. Alright, so this might be enough for video one. Well, a few more minutes maybe.
And doesn't want to give it up because it is a non-conductor. Friction can cause electric charge. And that's exactly what happens when I touch this balloon and try to discharge it through friction. I may actually have charged it. If I take these party balloons that all of you may have seen and you just rub them on your shirt, on your trousers, they stick to my hand. They have charge on them, whether it's positive or negative, I don't know, I don't even remember, it's not important. And so when I bring them to my hand is not a good conductor.
So again, it has nothing really to do with the conducting. It has to do with the fact that the atoms are polarized, and it's on an insulator, so they don't unpolarize or unpressurize easily. So it's just a two magnet scenario again, and so it's always magnetism that causes the attraction or repulsion. The electricity is conveying the pressure from one atom to another. Alright, so that's probably a good point to end video one, and we'll see how long I can do this and how far into it I'll go, and we'll see how it goes. And I'm not completely satisfied with the quality of the audio, so I might have to change mics again, but use the better mic, but you know, just a technical issue. We'll see how bad it is and such. So till the next edition of and such and so forth and whatnot. Thanks for watching.